Memory in C++ is fundamentally about managing sequences of contiguous bytes that your program can utilize. Now, this might sound a bit dry, but understanding how memory works is absolutely crucial for writing efficient and effective C++ code. In this tutorial, we're diving into how memory representation in C++ functions, exploring the various types of memory you'll encounter, and discussing how to manage this memory effectively. So, grab a snack, settle in, and let's get started. Now, let's take a look at a basic example of variable declaration and memory allocation in C++. In this snippet, we declare an integer variable named x and initialize it with the value of 10. This allocation reserves a specific amount of memory for x on the stack, allowing the program to store and manipulate this value easily. To illustrate how we can monitor memory allocation, the code utilizes the address of operator AND, which retrieves the memory address of variable x. When you execute this line, it will print out the actual address in memory where x is stored. Understanding how to access this address is vital, as it lays the groundwork for more complex memory management concepts. Alongside this, the code also outputs the value of x, showing that yes, we can easily work with the data stored in that memory location. This simple example not only teaches the fundamental concept of memory representation in C++, but it also sets the stage for deeper exploration into how variables are managed within different memory regions. Now, let's dive into implementing dynamic memory allocation in C++ using the heap. To start, we'll include the necessary headers and set up our main function. Inside this function, we'll first allocate an array of 5 integers on the heap with the new operator. This is fantastic because it allows us to define an array size that can be determined at runtime, especially handy when we aren't sure how big the array needs to be until our program is running. Next, we'll initialize this array by doubling the index values, which demonstrates just how easily we can manipulate elements stored in dynamically allocated memory. After that, we'll loop through and display each element of the array, showcasing the simplicity of accessing and using these elements through their indices. Finally, it's super important to free the memory we allocated once we're done using it. This is where the delete square operator comes into play. This cleanup step is essential to prevent memory leaks, which are a common pitfall when working with dynamic memory. By managing our memory properly, we'll ensure our program remains efficient and stable, balancing flexibility with responsibility in C++ memory management. From these values, the pie chart titled Memory Representation in C++ divides the subject into 6 labeled slices with the following proportions: stack memory 30%, heap memory 25%, pointers 20%, dynamic allocation 15%, memory leaks 5%, and smart pointers 5%. From these values, we can draw several conclusions. Now, stack memory is the single largest slice at 30%, and when we combine that with heap memory at 25%, we get a total of 55%. This indicates that raw storage regions form the majority of the representation on this chart. Next, we have pointers at 20% and dynamic allocation at 15%, which together make up 35%. This highlights that addressing and allocation mechanisms are the next most significant concerns in memory management. Memory leaks and smart pointers each occupy 5%. Now, you might think, oh, that's small, but they represent distinct topics. Memory leaks focus on a common failure mode, while smart pointers offer a mitigation and ownership strategy. Overall, this chart suggests a natural learning progression. First, prioritize understanding the stack and heap layout, then delve into pointers and allocation semantics, and finally, address leak prevention and smart pointer usage to manage ownership and lifetime effectively. This roadmap will definitely guide you as you navigate the complexities of memory representation in C++. Now, let's take a closer look at how pointers work in C++. In this example, we're going to start by declaring an integer variable, which we'll call value, and we'll set it to 30. Next, we introduce a pointer, ptr, which is initialized to point directly to the address of value using the address of operator. That's the ampersand. This example makes it clear how pointers give us a way to reference the exact location of a variable in memory. Now, here's where things get interesting. By dereferencing the pointer with the asterisk operator, that's the asterisk ptr, we can access the value stored in value. This concept is crucial, as it shows us that pointers allow for indirect manipulation of data, which can lead to more flexible and powerful programs. Also, if we print the pointer ptr, we'll see the address of value, showcasing how pointers serve as essential tools for memory management. So, this example not only illustrates the basics of using pointers in C++, but it also dives into the core principles of memory manipulation, a vital skill for any C++ programmer. Understanding pointers means you can handle and manipulate data efficiently, but a word of caution, mishandling pointers can lead to some serious errors and crashes. Always be careful with pointers as you dive deeper into your programming journey. Next, we will write the following code to illustrate a common problem in C++, and that problem is memory leaks. In this example, we have a function called createMemoryLeak. Now, what this does is it allocates memory on the heap using the new keyword for an integer pointer named leak. But here's the kicker. It doesn't free this memory using delete. Each time createMemoryLeak is called, it creates a new integer without any corresponding deallocation. This leads to increasing memory usage over time. Moving on to the main function, we've got a loop that iterates 1,000 times, repeatedly calling createMemoryLeak. This really exemplifies a scenario that could happen in a larger application if memory isn't managed properly. As a result, the program ends up with a whole bunch of allocated but unfreed memory blocks, which means we've created memory leaks. Now, the output memory leak created serves as a reminder of this issue, highlighting just how crucial it is to manage memory carefully. To prevent such leaks, developers should always ensure that any memory allocated with new is matched with a delete, or, preferably, use smart pointers that automatically handle memory deallocation when they go out of scope. This code effectively highlights the potential pitfalls of C++ memory management and reinforces those best practices we should all be following in programming. Now, let's take a closer look at how std_unique pointer works in real-life applications, which is really a key player in modern C++ memory management. First things first, let's include the necessary headers. We need std memory for smart pointers, and don't forget std_iostream for our output. Now, we'll declare a unique pointer called p1, and it points to an integer set to 10. This is a great way to show how unique pointer takes care of dynamic memory all on its own, allocating memory right there on the heap. Next up, let's use count to display the value that p1 is pointing to. You'll see that dereferencing it gives us the value, and we don't even have to worry about manual memory management. Now, here's where it gets interesting. The unique attributes of unique pointer really shine when we want to transfer ownership. To do this, we use the move function. By assigning p1 to another unique pointer named p2, we've effectively transferred ownership, which means p1 is now empty. This feature prevents multiple pointers from referencing the same resource, which is a huge bonus for reducing the risk of memory leaks and dangling pointers. So, in a nutshell, std_unique pointer not only simplifies memory management, but it also upholds the principles of object ownership, making it an incredibly powerful tool for C++ developers. Next, we will write some code to dynamically allocate an array of integers on the heap. This helps us store multiple values efficiently. First, let's declare a constant integer, size, which will define how many elements our array will hold. So, using the new keyword, we can allocate memory for this array. And we'll call our pointer myArray, which points to that newly allocated memory block. After we've set up our array, we'll initialize its elements in a loop, assigning each index a value that's a multiple of 10. This not only populates our array, but also lets us access each element using pointer arithmetic. Pretty handy, right? Since the memory layout is contiguous, it makes our job easier. Following that, we'll use another loop to output each value to the console, showing just how straightforward it is to iterate through and access those array elements. And here's a crucial tip. Once we're done, we must remember to free the allocated memory using delete dash. This step is vital to prevent memory leaks, an essential part of manual memory management in C++. So, by efficiently allocating and deallocating memory, we ensure that our applications run smoothly and responsibly. Now, let's dive into a class that shows us how to manage memory effectively using constructors and destructors in C++. Here, we're defining a class called myClass, which comes with a dynamically allocated array of integers. The constructor of myClass takes one integer parameter that tells us the array size, using the new operator to allocate memory for this array. This means we can store a list of integers whose size we decide at runtime, not during the compile time. Pretty neat, right? So, when we create an instance of myClass, the constructor kicks in to initialize the array, filling it with values based on their indices. This dynamic allocation, it's a powerful feature. Now, what about cleaning up after ourselves? That's where the destructor comes into play. It's called automatically when our object of myClass goes out of scope, freeing up the memory we previously allocated. This is super important to prevent memory leaks, which can really bog down your program. Finally, to see what's inside our array, we've got a method called display. This method outputs the contents of the array easily. By putting memory management directly into the class, we're making sure resources are handled properly throughout the object's lifecycle, which is a key element of programming in C++. Not only does this keep our code clean and manageable, but it also highlights the crucial role of resource management in C++. As we've explored how memory representation works in C++, it's become clear, thoughtful, that having a solid grasp on memory management is key to crafting efficient and robust applications. From understanding stack and heap memory to the careful use of pointers and ultimately leveraging smart pointers, each area lays the groundwork for mastering how to use C++ memory effectively. So, embrace this knowledge and practice with examples related to memory management. You'll find yourself becoming quite adept at it in no time. Just a friendly reminder, with great power comes great responsibility. And when it comes to C++, that responsibility really means keeping your memory in check. So, happy coding!